Log on, tune in, find out. Another good idea from Cambridge.
So, I was looking at the pictures that we took the other day and the one we took a few years ago. I wanted to see if I have changed. And actually, I haven't changed much. I have actually the same clothes, which is kind of the t-shirt. I can see the trousers. I know. Anyway, which is worrying. But the talk is different. The talk has changed. Okay. So, in the first part, well, in the talk you just saw, you saw the first step in distance-based tree reconstruction, which is about going from sequence data typically to a matrix of pairwise distances. Here I'll talk about the second step in distance-based tree reconstruction, which is about going from the distances to a tree. Okay. We can subdivide this step into a number of other components. The first component is simply to specify a way to fit the branch lengths of any given topology. So we have, here it's a 5 taxon case, so we have 15 topologies. We want to be able, for each of these 15 topology, to specify, to fit, to assign branch lengths to each branch, obviously. As we'll see, this can be done in a number of ways. So this is what happens once they are fit. Then the second component that we need to specify is an optimization principle that allows us actually to say which of these trees that we have generated are better than others, and to discriminate among them. Here, for example, I've chosen the shortest one. The principle that chooses the shortest one is called minimum evolution. Then, since the optimization problem that, the optimization problem that asks to find the tree that is optimal with respect to our principle is usually computationally hard, we'll need a heuristic to produce a good tree, which won't be usually optimal with respect to the principle. Well, sometimes it will be optimal, but it might not be. So this framework can be applied for every method in distance-based tree reconstruction, even neighbor joining, which wasn't thought to fit into this three-way division. For instance, for neighbor joining, now it's clear that the branch lengths are fitted using a balanced version of weighted least squares. I'm not going to explain what this is. The optimization principle is minimum evolution, so neighbor joining favors short trees. And the algorithm is what everyone knows by neighbor joining, is a heuristic that chooses at each step a pair of taxa to join based on the optimization principle that has been chosen. Okay, well, for more information you can look at this paper, very nice one. So I'll concentrate on the first component, which is about, as I said, fitting branch lengths. And so we have a distance matrix, we have a topology, we fit the branch length so that the distances between each pair of taxa in the resulting tree, these ones, are as close as possible to the distances in input. So these ones are the lengths of the paths between each pair of taxa, A and B. This is the length of this path here. And typically, we assign branch length so that we minimize this optimization of this objective function. This is called weighted least squares. And it's basically a weighted sum of the square differences between corresponding elements in the two matrices. Okay, and this is not a difficult problem. Actually, you can, well, it's not computationally hard. You can find the optimal branch length in polynomial time, in cubic time, but it's still not very good because when we use distance methods, it's clear we want something really fast. So we'd like to improve on that. And in fact, in some cases, you have ways to improve on that based on simple formulae that give you the optimal branch length to assign to the topology. Okay, so the simplest case where we have these kinds of formulae is ordinarily squares. So if you look at this, ordinarily squares is simply the case where the weights here are constant. So in this case, there are nice formulae, well, maybe not so nice, okay. So this is this gives the optimal length for an internal branch. There is another formula for external branches. I'm not going to show you that one. It's actually simpler than this one. Here we assume that A, B, C, D are the 4 clades at the corners of the branch. N, A, and so on are all the numbers of taxa in each clade. And the terms that I'd like you to concentrate on are these delta bar AC, delta bar BD, and so on. These are the average distances between pairs of taxa taken from the two clades. So in general, delta bar XY is the expectation, let's say, of the distance between x and y, where x and y are chosen uniformly at random from these two clades. Okay, and it's important here to notice that it's uniformly. So you just pick one. If there are n, you take one with 1/n of probability from that clade. Okay, there are other cases where there are formulae. I'm not going to show you those ones, but basically. A very interesting result for me, at least, was that all the cases where we have formula are particular cases of a more general framework, where the weights in this expression have a multiplicative form. What does that mean? Okay, I'm not going to lose time on this, but basically, if you know what additive is multiplicative, we say that a function of the pairs of taxa is multiplicative when the logarithm, when its logarithm is additive. And here we have a formula that is very similar to the one we've seen before. Again, we have these delta bar terms. We have these things. I'm not going to explain them. The delta bar terms now are defined in a slightly different way. It's again the expectation of the distance between two taxa taken at random from the two clades. But now the distribution is not necessarily uniform. And the great advantage of this formula compared to the standard procedure which goes through matrix calculations is that the optimal branch length can be obtained in quadratic time instead of cubic. This is actually doesn't seem like a great advantage, but it is, and it's optimal because obviously the input distance matrix is quadratic itself, so you can't do better than this. And actually, we'll see later in the talk that when we do something even a bit more complex than this, the difference between the two approaches becomes even bigger. So what I've been working on is a generalization of all these formula that we've seen before. I've just taken their form. So basically, I keep all these delta bar terms instead of having these terms. They multiply these other terms. I have simply a lambda value, which is a number between 0 and 1. Here 1 minus lambda e, So these lambdas depend on the branches. They can be assigned, each branch can have a different number. It doesn't matter. You can actually have no relationship between the lambdas at different branches. And now also the delta bar have a more general definition than before. It's the expectation again of the distance between two taxa chosen at random, but now they're chosen at random from x and y according to a random walk fashion. Okay, so what does that mean? It means that we assign at each bifurcation inside the tree, these are all binary trees by the way, at each bifurcation we assign a probability of going to the left and a probability of going to the right. And obviously, if we have these probabilities, this determines a distribution over the leaves of any clade. So when, for instance, the probability of picking this x from this larger clade is given by the probability of going left here, right here, and left here. Okay? And so basically, why am I defining this distribution? This is just a general form of all the distribution that we admit. Even the uniform distribution can be obtained with a, it's easy to see that can be obtained with a process like this. All the distributions that we've seen before, including the ones by Miaesco and Pachter, which I haven't described to you. Okay, so this is a very general form for this formula. And the nice thing is that this formula, despite they're so general, although they are so general, they have very desirable properties. And the first one is statistical consistency. So imagine that we use our formula to fit branch lengths, and we combine this with an optimization principle, a standard one like least squares, minimum evolution. Minimum evolution has more than one version depending on how negative branch lengths, because we can obtain negative branch lengths, depending on how negative branch lengths are counted. So in some cases, when you calculate the total length of the tree, you just add them all. In some cases, you just add the positive branches. In some cases, you add the absolute values. Anyway, you just need to retain that minimum evolution has lots of different versions. In any case, we have statistical consistency. What does that mean? We heard a bit before, but that means that as the input distances tend towards the real values, also the tree that is identified as optimal by the optimization principle that we have chosen tends towards the correct tree. This is actually a result that generalizes all previously obtained results of consistency for minimum evolution, also least squares, but it's kind of trivial for least squares. So yeah, this provides a theoretical reason why using our formula there is a nice idea. Okay, but I think that the most interesting thing is that these formula have nice algorithmic properties when you use them in combination with local searches, because they allow us to update branch lengths really efficiently. In local searches, we basically do some simple moves. For instance, NNIs. Here I'm talking about NNIs. We've seen them in Catherine St. John's talk. I'm not going to say what they are. It's not really important in this case. But basically, what you do is that at some point in your local search, you have some tree, and you want to visit the neighboring trees. So these are the neighboring trees, and you want to calculate their branch lengths, because that's what allows you to judge if these trees are good or not. So using the normal matrix-based algebra solution is going to require a cubic amount of time for each of these transitions, so n O of n to the fourth in total, which is very slow. So the good news is that in the case of when we use our formula, we can actually calculate an intermediate data structure, in quadratic time, and then use this intermediate data structure to calculate all these branch lengths, in each case in linear time, which gives in total a quadratic time, so which is optimal because the input distances are quadratic. So we can visit all the neighbors in optimal time, and it's much faster than traditional matrix calculations. Okay, so I'm finished. The conclusion are there is a novel class of formula. It's just simply a generalization of everything we've seen before. They generalize things that have that are statistically well motivated. I haven't spoken about this. We showed that statistical consistency holds when you use this formula, and you can combine them quite easily with local search. And that's all. Thank you.
We have time for a couple of questions.
So have you got any reason to want to use different lambdas than you would get out of ordinary least squares and bounds?
Probably not. So what we will do next is try and use the multiplicative models by Miesco and Patte, which give different lambdas, and we'll use those. We won't use arbitrary lambdas. What I find nice is that we have consistency results for any lambda. So I like to make the proof as general as I can. So that's it. But who knows? Maybe some things that I haven't thought of. Maybe it's good to have a general result.
Does it all work for SPR moves too?
I don't think so. Well, yeah, maybe, but not in quadratic time. Maybe in cubic. Well, yeah. Cubic time.
You ever thought about considering a problem where you don't have compatible splits, but you have incompatible splits? You want to do something like NeighborNet, where you have to come up with edge lengths?
One day. One day.
Okay, if there's no further questions, let's thank the speaker once again.